It's a great pleasure to have Brendan Guilfoyle here, and he will tell us about mean curvature flows as part of the proof of the calculator.
Okay, so thanks for the invitation. So I'm going to talk about curvature flows. And so, as before, this is joint work with Bloomberg. And it's based on 3 papers that over the last, I guess, 5 or 6 years. The first paper has appeared, the second one is hopefully about to appear, and the third one is hopefully about to be written. So the outline of what I'm going to talk about. So the first thing, I'm going to give a little bit of motivation for the type of question I'm going to be addressing. Secondly, I'm going to talk about the geometric setting, and then finally I'll come back to discuss the topic, which is these particular examples of curvature flows. I'll probably give more details about the linear, and then I'll also talk about the non-linear case. So the first thing I want to talk about is just where do these kind of equations, or what I'm going to talk about, where they arise. So let me just talk about, for motivations, let me talk about there's 2 primary motivations. The first one will be physical. So there's a number of physical problems in which curvature flows naturally appear. The first one would be if you think of a pebble, say on a beach or at the bottom of the sea. So it's some irregular shape, and it's being abraded, being rolled around, and the corners are getting knocked off, etc. And what you get is a surface. If you just think of the surface of the pebble, and you think of it changing over time, and it's going to change in a way that's related to the curvature, because, for example, the pointier bits are going to get worn off quicker, and it's going to be modelled essentially by a diffusion equation on how this surface changes in time. It's one example of the kind of equations that appear that I'll be talking about. I'll write them down more explicitly in a minute. Another situation would be, say, cooling, or maybe melting is probably a better word to say. If you look at it, say, a melting cube, again, you have some kind of surface, and the surface is changing in time as it melts. And in particular, you notice that the corners, again, somehow will get melted off quicker. So this is called a Stefan problem, classically. And I guess the third motivation, maybe helpful to throw in as well, is that in computer graphics, often you have some surface that you've rendered from some data, and it's a bit too rough, and you want to smooth it. So, in fact, if you look at smoothing in graphics or in CAD, again, often the way you change the surface by something that kind of smooths it out, and it's usually can be well modelled by a diffusion process. So what these all 3 have in common is essentially that you have a surface is changing, where the rate of change of your surface is proportional to what? Well, some function of the curvatures. So again, just function of curvatures. So the curvatures of the surface are determining the flow of the surface, or the way in which it's changing in time. Now, those 3 examples then show you that you kind of might be interested in looking just generally at a surface where you're flowing it by some function of its curvatures. And this is exactly the type of equation we want to look at. So we want to look at a surface where, say, x is the vector, the position vector. So you have your surface in R3, and a point on the surface is given by vector x. And these curvature flows, which we describe all of these situations, will be ones where you have K1, K2 times the normal, the unit normal to the surface at that point.
What's x again?
X will be your position of the surface, then you project it perpendicular to the surface, and you want that will be in the normal direction, and you want that rate of change to be proportional. You might have a minus in there, usually. Where K here is a function of the curvatures. And these are the types of equations that would model all three of those situations. Depending on which function you choose, you might have different types of abrasion models. It's different when something is rolling around the bottom of the sea as against up on a beach or in other physical situations. So you might choose a different function of the curvatures of the surface. K1 and K2 are the curvatures. Now I'll talk a little bit more about the curvatures and exactly what such equations look like in a while, but that's the general, this is what we call a curvature flow. Right? So this is a general curvature. Now, often you might think it in higher dimensions, this could be generalized to n dimensions, but I'm only going to be interested in this physical situation of a surface in a three-manifold, in R3 in fact. And you can generalize this in lots of different ways. And these kind of flows have been discovered, or have been investigated a lot. Special ones have been looked at a lot. Examples include, say, mean curvature flow. So mean curvature flow would be one where so mean curvature flow would be one where you flow by the average of the curvatures. You can also look at, say, Gauss curvature flow, where you flow by the product, etc. So there's lots of different choices there as to what kind of. For example, the pebble on the beach, one of the ones that's used is what's called a Bloor flow, which is a linear combination of curvature, of Gauss and mean curvature. In fact, so again, there's different possibilities. These turn out to be kind of easy because they're homogeneous in the variables, so that's a good thing about these equations. But in general, what I'm interested in is where this is just an arbitrary non-linear function. I want to try and understand that to some extent. Okay, so we'll talk. So again, this is a second order. This is a second order system because K1 and K2 will be second derivatives. It's got two variables because you're looking at the flow of the surface. And I'll talk a bit more about the different types of equations that can arise depending on K in a minute. Okay, so that's one motivation, if you like, physical, and I'm going to look at this equation from a different point of view, and it's the following. So this is a more mathematical question. So first of all, let's just say that, so if you have a surface S3, and we say it's Weingarten, so we call it a Weingarten surface. So if there exists some function k from R2 to R such that k of the curvatures, I could say 0, or you could put that on the other side. I'm going to just put that on constant for a reason we'll see in a second. So if you like, again, you could take this constant here and put it on the other side. You can see these would be the stationary solutions. There'll be ones where there exists already a k in which, right? So this would be kind of like the stationary solutions. Okay. So again, the curvatures K1 and K2 of a surface, if you look, for example, at a round sphere, the curvatures are constant and equal. They're equal to 1 over the radius of the sphere. And so this would would satisfy this equation for any k. So round spheres satisfy an equation like that. No matter what k you choose, it will satisfy that relation. Right? So round spheres are not very interesting in some sense. We're more interested in non-round spheres. Okay, so what kind of questions would you have? Well, I mean, examples of this, within classical surface theory, studying special cases of this, for example, studying minimal surfaces is where you're choosing the mean curvature to be 0, for example, or constant Gauss curvature would be where you're assuming that the Gauss curvature is constant, or CMC surfaces. So all of these different classes of surfaces that are often quite interesting mathematically are examples of Weingarten surfaces. You also have other examples. I'm sorry. Yeah.
Soap film bubble surfaces.
That's CMC. They're constant mean curvature. Soap films are minimal, so bubbles are constant.
Okay.
Yes. So they're models for lots of different things. And other examples of Weingarten surface include any rotationally symmetric surface. So, for example, if you take a rotationally symmetric surface, well then, there's only one variable, right? So it only depends on one, so you can always, the two curvatures are going to have some relationship between them because they're functions of a single variable. Might not be easy to write it down, but there will be some functional relationship between the two if there's only one variable involved. So rotation symmetric surfaces are examples of Weingarten surfaces. If you take any curve and you take just the tube over a curve, it's another example. So there's lots of, so tube over a curve. So you take any curve in space and you take a unit distance all the way around it, you get a torus, and that tube will be, that surface will have some functional relationship. Again, very hard to work out what exactly the functional relationship is. However, they're examples of it. Now, the question that I want to think about, again, this is the mathematical motivation in some sense, what we're going to talk about in a minute, is to ask the following question. So what possible Weingarten relations, so functions of the curvatures, can exist for non-round. So again, as I said, round ones are not interesting because the two k1 and k2 are constants, so that's true for any function k, right? So it's not so interesting. Exists for non-round, and I'll throw in convex spheres, so topological spheres, smooth or whatever. So what possible Weingarten relations can you have for spheres? Now, what turns out to be kind of an amazing fact about that question is that it has a topological dimension and it also has an analytic dimension. And in particular, just a very simple thing, if you choose a smooth sphere, you have certain relations that can hold. If you want a real analytic sphere, one where it's real analytic and right in terms of power series, well then it restricts the number of relations that you have. So again, the exact differentiability of the sphere, as well as the fact that it is a sphere which is topological, restricts quite dramatically which functional relations you can possibly have between the two curvatures. Okay, so what I want to do then is look at, is to address this question using a curvature flow. So before we need to do that, let me just mention one or two classical results from the 50s actually. So one is the following. So this is Hartmann and Wintner, 54. And there are other papers and similar ideas by Chern and by Hopf, again from the 50s. And it is the following. So let me get the exact wording. So any sphere satisfying k equals 0 or constant, doesn't matter whether you put the constant 0 on the right hand side, any sphere satisfying that, where k, now just to go back I guess perhaps, what type of equation is this? Well, this equation, again, it's a second order equation because k1 and k2 are second derivatives, and it's fully nonlinear. It's just a fully nonlinear second order equation because we're choosing any function there. Now, what they say here in Hartmann and Wintner is where k is elliptic. In fact, it doesn't have to be elliptic everywhere. In fact, it only has to be elliptic at a single umbilic point on the surface. So again, if you recall from my talk yesterday, I'm going to talk a little bit more about that. An umbilic point is where the two curvatures are equal to each other, so it looks like a sphere. Okay, so if you have any sphere satisfying a relation where k is elliptic at an umbilic point, then it's round. Everything.
What's your definition of sphere?
Sphere is topological sphere, so I'm just talking about an embedding of S2 into the. So when I say the word sphere, I do not mean round sphere. I'm using round as the right because I could put topological sphere every time, but that sounds a little bit over the top because I want nice smooth and I want embedded. Right, so it's an embedded sphere. Okay, so again, what does it mean to be elliptic? Again, that's just a straightforward thing. I mean, what kind of equation? So if you have an elliptic equation, what do you mean? Well, the model for an elliptic equation will be just d2x squared plus d2 dy squared. Just looks like Laplacian. The symbol is invertible. There's different ways to define it, but this is what we mean by being elliptic. It behaves like, it looks like, you can use the maximum principle. It has nice properties. For example, the other thing that could happen, you could have a hyperbolic relation. K could be hyperbolic, which means, I mean, we may have a non-linear relations here, but the typical one, the linear case, again, you would something like this. Now, of course, these are fully non-linear, so it's really generalizations of this that we want. But just to keep in mind, that's the model for your elliptic equations, and this is the model for your hyperbolic equations. And what this says is that your elliptic equations, basically, you can't have, the only ones that satisfy an elliptic relation are going to be round. So we're not going to find any solution, any answers to this question if we restrict to elliptic relations. Okay, but what we're going to talk about is the following insight, which is what we're going to do is, so we'll try to find spheres satisfying k equals 0 by flowing. Again, that formula I wrote down a second ago, minus k. So this is the idea of what I'm going to try and do. I'm going to try and show there exist solutions, round spheres, or sorry, non-round spheres, I should say spheres, that satisfy this relation by flowing to it. Now, what we would like in optimal situations would be this be a nice parabolic flow. If this was a hyperbolic flow, you usually have problems. You can get blow up, you're not going to be able to use this as a nice tool. You want elliptic methods to show existence of solutions to such an equation. So you would really like this to be elliptic, and then this will be a parabolic equation and have a standard kind of approach to it. You can't, or at least you can, but the problem is the best you're only going to get by Hartmann and Wintner is round. You're not going to get a non-round solution. So this is, and it turns out if you look at, say, mean curvature, if you look at Gauss curvature, they're all elliptic. So the best you can do, if you do mean curvature flow, which is all the rage these days in geometric analysis, if you're going to do mean curvature flow or you're going to do Gauss curvature flow, the best, in some sense, you're going to get is round spheres, or it'll blow up. You know, you're going to have one or the other. You can't really get anything that's not round at the end of it because there are no stationary non-round solutions. Okay, the insight is the following, is that if you restrict this equation, where, say, this function is a function here, we would be looking at it applied to a function of x and y, x and y. If you assume that this doesn't depend on y, well then you just have one variable, and then this will become elliptic, this will become parabolic again, but parabolic with one less space dimension. So for rotational symmetry, it depends on k. Now there's some restrictions on k, not every k will work. We can still get, even though it's not parabolic in the two-dimensional sense, it's hyperbolic. Because this is 0, then your symbol is still one, has got the right dimension and it's not degenerate. So we can still get parabolic flow. So this is a parabolic flow in one space dimension. Instead of being in two space dimensions, it'll be in one space dimension. Okay, so then you can see we actually do have a chance to use a parabolic method to find a solution to a hyperbolic equation, which could actually then answer questions about what possible Weingarten relations could be satisfied by closed round spheres. Closed non-round spheres. Yeah.
Is it a ellipsoid, a closed non-round sphere?
Yeah. But actually, an ellipsoid does not well, the non-rotation symmetric ellipsoid is not Weingarten. There is no functional relationship between its curvatures.
Okay, so if I could get an ellipsoid, so rotation like in SO3? Like
rotation symmetric, so a rotation symmetric ellipsoid would look like this, so it would just be x squared plus 2y squared plus 2z squared equals 1, for example. It's rotationally symmetric.
Yes, yeah.
But if you were to do this 3 times this, then you get something that has 4 umbilic points, and that doesn't satisfy functional relationship. So the general triaxial ellipsoid is not Weingarten. Right, but the rotation symmetric one is, or any rotationally symmetric surface is. Yeah. So, yeah, you might ask the question, is there any stationary non-round solutions, for any Weingarten relation? So I'll show you exactly one class in a while, and some of the properties that they have was quite interesting. So what we're going to do is we're going to just look at rotationally symmetric curvature flows. We're going to allow this to be hyperbolic, but then when we do the rotational symmetry, we'll still end up with a parabolic flow. So that's the basic idea. Now, what happens is it turns out to be it works better than one would have expected, and the equations decouple. I mean, you can see it there as a kind of a system and it looks messy. But in fact, the whole thing decouples and becomes quite nice and tractable. Okay, but before I can discuss exactly how it becomes tractable, we have to get a bit more of a picture. And so the second part I want to talk about is the geometric setting. And what this allows me to do after this will be to show you exactly how the flow goes in certain cases directly by pictures. You can actually see exactly how the flows behave. And some of the behavior is quite amazing. So let me just start out again, just to start here in R3, we have, well, that's not convex. We'd like to have convex. It doesn't have to be convex, but let's take a sphere. And again, remember you have a point, you have your normal to the sphere, and then you have the tangent space, and then most importantly for us, we have the second fundamental form, which is a 2x2 symmetric matrix, which we can diagonalize, and these are the kappa 1 and kappa 2, which are the eigenvalues of the second fundamental form. And then we have the umbilic points, as we mentioned earlier. The umbilic points were the points where it looked like a sphere. It's when the two curvatures are equal to each other. In fact, what I'm going to be interested in, it's easier to see it by the radii of curvature. So this is just the relationship between, for example, in a circle between its radius and its curvature. So in fact, what I'm interested in is R1, which is 1 over K1, and R2, which is 1 over K2. So these are just the radii of curvature rather than curvatures themselves. And secondly, I'm going to do a slight change of coordinates once more because things will be a lot nicer. So first I'm going to take the average of the radii of curvature and the difference. And I'm going to assign an S. Again, just rotations of 45 degrees. Okay, and then what I'm interested in is we have a surface S contained in R3. And I want to look at the map that takes S into R2, which takes the point on the surface to its curvatures. So, it's radii of curvature, sum and difference. So psi of P and S. Okay, and I want to try and get a picture of what that map looks like. So it takes a surface and maps it into its curvature space, right? The space of curvature. In fact, I tend to call this the radius of curvature space. And okay, so it starts out just as R2. So let me show you more or less what it looks like. First of all, you have the umbilic points. Now remember, the umbilic points are where these curvatures are equal to each other, the radii of curvature are equal, so that's when S is 0. So that's your x-axis, if you like. So here, you have your umbilic points. In fact, I like to call this the umbilic horizon, in a sense, and you'll see exactly why when I geometrize this picture. And then what else do you have? Well, you have the origin where both curvatures are 0, but more importantly, you have a kind of a right angles. If you want to say convex, you would like the curvatures to be both positive, R1 and R2. And that means it's actually inside of this here. So the convex are going to be in here. Okay, it could be on the other side either. I'll choose them to be on that side. R1 and R2 being positive means you're inside of that triangle. So that's exactly where your map is going to end up. So what does a generic surface look like when you look at its curvatures? We were just looking at its curvatures. There's radii of curvatures. Radii of curvature. Well, the general one, so for example, I drew it a second ago, you have a generic one will have 4 isolated umbilics at each of index 1/2. So it will cross this at 4 points. And so it will be able to be up here, And it doesn't have to be smooth, and it can kind of fold over on itself and do all kinds of funny things and look like that. So this is a map from S2 onto the plane, and it's going to look typically something like that. Right? So that's your average curvature diagram or radius of curvature diagram for a surface in R3. Now what we're interested in though is more interesting than that, because we're interested in rotational symmetry. Now, what is Weingarten surface going to look like? A Weingarten surface is going to look like, its image is going to look like a curve in this space. Okay? Because there's a functional relationship between the two curvatures, between the radii of curvature. When it's rotationally symmetric, that's also the case. So what's a typical rotationally symmetric surface look like? Well, let me just show you what a typical rotationally symmetric surface looks like. For example, looks like that. That would be one example. So that would be an oblate sphere. I've chosen a certain way to... so you have two umbilic points, one on the top, one on the bottom. These are here and here. They're your umbilic points. And you have a rotationally symmetric. And each point in the interior has a whole curve worth of points that it comes from. So that's a Tralee, like the Earth would look something like that, a simple rotationally symmetric model. An oblate surface would look like this. So this is oblate. What would that look like? Well, here, if you like, the R1 and R2, that's the opposite direction. It's going to look something like this. And again, the two umbilic points here and here.
I think the oblate and pronate switched. Oblate on the left.
Sorry, it's going to be above or below, so it's just a choice of which if I chose R1 to be the profile curve, yes, but I've actually chosen R2 to be the profile curve. It depends which you choose in the rotation symmetric case, whether you choose it to be the curvature of the profile or the curvature of the rotational symmetry. It depends which you choose. But it'll just flip the picture above and below this umbilic curve, this umbilic line. And again, if you have something that's turnip shaped, right, so it's kind of pointy at one end and oblate at the other, well actually somewhere in here it's going to have a whole circle of umbilics, and what it's going to look like is something like that. Or a piece of it stuck above it, right, so this is like the prolate piece up here, and this is oblate, it's down here, and where it crosses here is a whole circle of umbilics. Right? That's a whole circle of umbilics. Okay. So again, this is just to get a picture of what a surface looks like in curvature space, in radius of curvature space. But what you find is quite an amazing thing is that the umbilic points, which are down here on this line here, that the slope at which the curve comes in is quantized. It's quantized if it's a smooth surface. So let me state a couple of amazing facts about these diagrams. So let's just take a C3 smooth surface. Oh, and I should say, let me just write it for non-round silver surface. So it's not umbilic everywhere. So again, sphere, I probably should say sphere, but again, this is a kind of local thing. Actually, no, let me just say sphere to be 100% sure that it's correct. So satisfying a real analytic Weingarten relation. Has the following property. So again, assume this is k equals 0, I suppose, probably. K equals constant, k equals 0, doesn't really matter. It's real analytic. So the surface is itself real analytic, meaning that it can be written in terms of power series overlapping with the real analytic functions. So the surface is real analytic if and only if the derivative of the functional relation in the direction of this s variable, the second being the difference between the radii of curvature, that at the origin, and when s is 0, this means when s is 0 I'm talking about an umbilic point, it's 1 plus 1 over n plus 1 for some natural number n. So what that's saying is that if you have a real analytic relation, your surface is real analytic if this thing here has a kind of an integer slope. This is like the slope of the relation at the umbilic point, evaluated at the umbilic point. Okay, so what we find is that for real analytic surfaces satisfying real analytic relation, you have this quantization, integer slopes at the boundary. Right? This is one deep fact from the Codazzi minority equations and their behavior around umbilic points, isolated umbilic points at the boundary of these Weingarten surfaces. Okay. Now, as we'll see, when we do our flow, this integer is going to be extremely important. The exact value of that integer will determine, in some sense, the behavior of the flow. Okay, so the second thing, I suppose I could also say it's real analytic. In fact, you can go a little bit further. It's C3 plus n plus alpha if and only if, in fact. So you can actually take Holder, you call it a Holder. It's in the right Holder space if it's 1 plus 1 over n plus 1 plus alpha, where alpha is between 0 and 1. So you can tell the regularity of the surface explicitly from the slope at which it hits the boundary. And if it's an integer slope in this sense, then it's real analytic. And if it's not an integer slope, it's got this alpha here is in 0, 0, 1, well then it gives you exactly the Holder exponent that you need. So this is the first amazing fact. And then the second amazing fact is the following, is that, well, we've reduced, if we look at, say, rotationally symmetric, so if S is rotationally symmetric, we can say a little bit more. In fact, we can relate this to something else. So if we take, and it's rotationally symmetric, we can do a Fourier decomposition. And in fact, we do the Fourier decomposition on S, on this difference between the radii of curvature. This is the key quantity in everything that follows. So when you write the Fourier decomposition of this, well, because it's on a half circle, right? Because you've got a rotationally symmetric surface, so you only need, an angle theta, right? And your theta goes from 0 to 2 pi. Right. So in that case, you've only got you can do it on a half decomposition. So L equals 0 to infinity, and here we've just dl cosine theta, and we write a sine of 2L plus 2 theta. So first of all, when theta is 0 or pi, you're at the umbilic points. So this has to vanish at 0 and a pi. Right? So we have the lowest order term is sine squared. Turns out it has to be sine squared for this to be a smooth surface, or to be at least to be C2. And this here, so again, maybe I'll just call all that AL, it's not so important. It's the order of vanishing at the umbilic points. So if you take that, so suppose that in this decomposition here, suppose these are all 0 except up to some value. So suppose this is sine to the 2k plus 2 theta. So it has the lowest order term. It has to vanish at least quadratically, but suppose it vanishes to higher order, plus higher order, 2k plus 4. Then this slope, again, the slope up here is going to be 1 plus 1 over k plus 1. Then mu equals 1 plus 1 over k plus 1. Here, I guess, this quantity here, I'm going to call mu. It's exactly this slope at the boundary. Describes the slope. So what we can see is, in fact, the slope at the boundary, which is quantized, is related to the order of vanishing of this S at the point. So we have a new relation here. So the order of vanishing, so exactly how fast it becomes umbilic, the order of vanishing of S is completely the same as the slope of the boundary. The slope at this umbilical horizon. Okay, and this is why it's quantized in some sense. This is why this is an integer when you have nice functions. Okay, so let me try now to motivate how we can use this to see how how this surface flows. What we're going to do is we're going to track the flow of its curvature. In fact, what we do is we follow the curvatures, and as we do, we integrate back by what's called quadratures, and you can reconstruct the surface from its curvatures. That's essentially the idea of what we're going to do. Okay. So let me now talk specifically. This is the setting, and I'm going to talk about what happens for curvature flows. And the first thing I'm going to talk about is just the linear case. So what do I mean by linear case? So suppose your k is just a linear function of psi and s. So in fact, what I'm going to assume is k is just the mean radius of curvature plus lambda times the difference. And we need a constant which I'll call psi infinity, just a constant, positive constant. Lambda is going to be bigger than 1, and psi infinity is some positive constant. Okay, so the first thing we'll say is are there any stationary solutions of this equation? And the answer is yes, there is, and this is Hop, again from the 50s, it's in his book, so I think the book has been published a number of times. Anyway, so the classic example, so there exist non-round spheres satisfying k equals 0 with this linear relation. Moreover, and again, as we said, if lambda equals 1 plus 1 over n plus 1 for n is an element of, well, so let me say lambda is equal to that, if and only n, if and only if the surface is real analytic. Your surface is real analytic. And not the differentiability we talked about. So again, you have this linear relation, and if you've kind of got an integer slope, then you have real analytic solutions. If you do not have an integer slope, if you have here this not 1 over 1 plus n plus 1 as we have here, but something else here, well then you do still have solutions as long as lambda is bigger than 1, but they're not real analytic. They're only smooth or have certain degrees of cold irregularity depending on the size of this n. Right? So what you find is that the coefficient in these Weingarten relations, that the underlying surface is extremely sensitive to it. And it's sensitive to it at the level of whether it's real analytic and smooth. That distinction, which is kind of hard to grasp in surface theory, somehow it comes in very strongly here in these real analytic, in these linear Hopf spheres. We call them integer Hopf spheres, when this has got this nice integer value. Okay, so let me now, so what the question is, here's some nice targets. These are non-round spheres, they satisfy a relation. Can we get to them using a flow, right? So we haven't mentioned the curvature flow. So here, this is the theorem from myself and preprint 2017. So curvature flow with, so the k as above. So take this linear flow, and I'm also going to take, and lambda is 1 plus 1 over n plus 1. So I'm only going to take the integer flow. So you're only allowed to flow by a functional in which this coefficient has this integer value. And let me also assume we need something about the initial. So initial smooth sphere, S0. As we said here, we call this of order k. It means it falls off at the umbilic points to order k. Of order k. So the falling off of the umbilic point of the difference between the radii of curvature at the umbilic point is order k.
What is S0 again?
So your initial surface. Your initial closed convex sphere. not round obviously. Just take a nice round sphere and assume it's of order k, meaning that it falls off at the umbilic points, order k.
And not round.
Not round. Otherwise, this would be 0 the whole way.
Okay.
Right, so that's assumed non-round. Okay, so then what we find, we have 3 cases. If the integer in the flowing equation is bigger than the order that falls off, then the flow explodes. Then the surface exponentially, the sphere this is, exponentially goes to infinity. Goes to infinity. So your sphere just goes out to infinity. It might go inside out, it might do something kind of strange, but it goes off to infinity. The second thing, if the two are exactly the same, then the sphere converges to a non-round top of the sphere, one of these examples. And the sphere converges to a non-round hop sphere, one of these ones I mentioned here. You can write them down explicitly in terms of integrals of functions in closed form. So, and finally, if the third case, what happens if your n is less than k? Or is it the, I think I've got it the right way, make sure. Oh, sorry, no, I didn't get it the wrong way. K, sorry, excuse me. And less than, we'll see in a minute why that's the case. If n is greater than k, then the sphere converges to a round sphere. Then it converges to a round sphere. Okay. So what's that saying? That's saying that the complete dynamics of this flow are determined just by the slope of at the umbilic horizon. The umbilic points and how fast it falls, that's all that matters. And if it's less than, well, you're going to blow up. Or sorry, if this order is bigger than it, it's going to blow up. If the order is equal to it, then you get convergence to non-round. And if you have the other way around, it's going to converge actually too quickly to a round. It's just going to go down to a round sphere. And the 3 pictures you can, right, you're heading for a linear relation, so it's easy to picture what's going on. And the picture is as follows. So in the 3 different cases, for this first one, you have here's your relation, let's say, that's your linear relation that you're trying to head towards. And then you start out with one that it's got a bigger slope. Well, then this is going to go out to infinity. It's going to blow up. It might pass through it. The whole thing just expands in every direction and goes out to infinity. Because the slope here is bigger than the slope here, right? That's this first case. If the 2 slopes are exactly equal, right, so these 2 slopes are equal and they're equal to this here, well then it's going to converge, and it converges explicitly onto this straight line. And finally, if this thing kind of is much sharper, and this one here is, well, sorry, it's even sharper, I should say, then this thing is going to go into the sphere. The sphere is going to be just a point on this. It's going to just be a point, so it's going to converge into that if it pinches over more. So these are the 3 cases that we have there. Okay, and let me just very quickly explain where does that come from. So the proof is just explicitly integration term by term. We actually, because this is linear, it turns out the equation. So the flow reduces to the following equation. I can write it down quite simply. So ddt of s over sine to the 2n plus 2, or no 2, sorry, n plus 2 theta. So if you just look at this flow of that quantity, what you get is the equation just becomes 1 over 2 n plus 1 times a second order differential operator on the same function, where this here is the associated Legendre operator. So its kernel is the associated Legendre polynomials of degree n plus 2. So associated Legendre second order operator. So it's exactly the order operator. And so what you can do is you can write it out in terms of bases. It's a little bit tricky for some parts of it, but you can do it in terms of bases. You can integrate term by term, and then you can actually get the exponential coefficients in time of exactly how they behave. And what you find is that your function, if you start off with some initial one, S0, so it's some A1 times sine squared theta, the lowest power that it could vanish is this, plus, and then you have the middle one, which would be the middle one when you have an n, so this would be an sine to the 2n plus 2, and then theta, and then you have the higher one, an plus 1, onto the 2n plus 4, plus dot. So it turns out when you do this, this here has a divergent exponential. So you have an exponential in time here when you integrate it, which has a positive power. So that explodes up exponentially. This part down here exponentially decays. Okay, and this middle bit here, this gives you the convergence to non-round. If you only have that. So it just depends on your initial surface. If it has no coefficients here, and this is the order, if it has exactly the right order, it will converge. These will all decay and they'll be gone. If that's gone, then it'll go to a round sphere. And if you have earlier terms, well, these are going to blow up. So that gives you the decomposition, how you get these three different types of behavior from the PDE. Precisely from that. Okay. So one of the good things about this, I guess, is that you can't often explicitly integrate these kind of equations. And not only that, but originally I had found I was getting very good convergence in general settings. And then I started looking at the linear case and I realized, oh, hang on, there's an extra subtlety here with regard to exactly what happens at this boundary condition. Now normally when you're flowing a sphere, you don't have any boundary conditions. But if you do it in curvature space, you're actually flowing a curve with boundary conditions. So it has a little bit of extra subtlety in it. So let me just now see how essentially this, where you can explicitly work out the solution, then tells us what happens in the more general case. And I'll answer a little bit of the question what's stated in one theorem. So again, this is myself and Wilhelm. So this is so it's the following. So remember the original question in terms of mathematical motivation was what kind of Weingarten relations can a closed non-round sphere satisfy? That was the, if you like, one of the motivational questions. We knew it couldn't be elliptic. We knew it couldn't be elliptic because by Hartmann and Wintner, etc. So here, what I'm going to do is give you exactly a kind of a complementary result of exactly what ones can give you non-round solutions. So let K, so we're talking, again, we're just taking an arbitrary smooth function. Generally, I will take it smooth. I'll ask it to have a couple of properties. The first one is I'll look for it to be a graph. So again, it'll generalize what I just did up here. When this is a linear function, you'll just get this flow I just talked about a second ago. L here is allowed to be any function of S. We'll just write it as a graph. The second property we want is that the slope at the boundary is an integer. It made a big difference here. I didn't say what happens if you flow without an integer. Lambda has to be equal to n, right? There has to be an n in here, right? Otherwise, you're not going to. So here, the same thing here. For this thing to be the slope at the boundary here is the derivative at 0, and we want that to be quantized. Right, so we want this integer in the linear term, so n and element of n. And then thirdly, okay, so now we need some second order condition in order to get this to still behave like the linear case, and that is that the second derivative at the origin be positive at the umbilic point, the second derivative of this Weingarten relation. Okay, if you have all of those three, then implies there exists, I think it was C4, yeah, there exists a C4 alpha, convex, closed convex sphere, satisfying K equal to 0 or k equal to constant, doesn't make any difference, you can absorb that into the definition. And if L is real analytic, so is this. So in fact, it's because we have a quantized slope, we're assuming that we have this quantized slope, so when we end up getting to this final solution, it's going to have a quantized slope, and if your relation that it satisfies is real analytic, well, then it's going to be, yeah.
What is alpha?
Okay, so alpha can be anything from 0 to 1.
So what is a C for alpha?
Yeah, it's just older. It's just, yeah, it's got bounded derivatives, yeah, with any alpha. So alpha is in 0, 1. Yeah, so that's the best you can do. Essentially, it's a convergence result. Actually, so this is your surface. The curvatures are going to be two derivatives, so it's C2 alpha. So you just use parabolic regularity. You get a C2 norm, and then you can get C2 alpha just by parabolic regularity. It's a little bit better. I mean, I guess slightly technical. It's not strictly necessary. But anyway, it's reasonably smooth. It's as smooth as you need for the differentiability, for the, to pose the problem, which is what we would like. And it's almost an exact counter to Hopf. So Hopf said if your relationship was elliptic, then it had to be a random. So what this is saying, more or less, very close up to this integer slope, is that if it's hyperbolic with an integer slope, then you can find a non-random. So it's exactly the kind of, it's the counterpoint, if you like, to Hopf's result. Okay, so how do we go from here to here? Well, once you know what happens in the linear case, it gives you a good idea of what to look for. So you start out with one that has the right slope, that has n equal to k, and then you use the maximum principle. So basically the proof, instead of actually being able to integrate the equations, you can still control it enough and control the derivatives, and once you can control the derivatives, you can go to a weak subsequence, and then you can end up with the solution in the right Holder class. That's the basic idea. So the proof uses maximum principle, and then and parabolic regularity. Some standard results. Once you can make it strictly parabolic, then you kind of get a lot of free theorems that people have put together over the last few decades, I suppose. Sorry. Okay, so at that point I think I'll test your pace any further. Thank you for being here.
Any questions?
You didn't mention it as an application, but is there a connection with Healy-Shaw flow?
I've never heard of Healy-Shaw flow. Could well be, yes. Could well be. Healy-Shaw. And where's that
It's
going?
kind of, so you have a surface which is formed by a block between two plates.
Okay.
You inject, and then the surface will be a curve in that.
Okay.
It's kind of two-dimensional. And then when you inject, there's a flow of the boundary.
All right.
I think there are analogs in R3 as well. But the evolution of the surface is something to do with the curve.
Oh, you related to the curvature? It could well be. There are other flows that are not curvature flows. Curvature flows do appear naturally in lots of places. That sounds like it could well be another place. What I have found is that, in fact, you can choose different curvature functions. And there's one curvature function that you can choose that essentially turns this into a one-dimensional porous medium equation. So, there are links to kind of disparate areas. Just if you take the right curvature function, it starts mimicking some things. Now, of course, it's one space dimension, so maybe that's not so interesting for people who work in those areas. But it's interesting that you end up with from these geometric equations on surfaces, you end up with these kind of interesting physical equations, or at least something quite close to them.
Just one, in physics literature, solid state physics literature, people often look at these crystal growths.
Okay.
And there's something called Wolf construction.
Wolf?
Yeah.
Okay.
So, you can find in Wikipedia.
Yes.
Some of these things actually sort of have this similar flavor.
So it could be.
Yeah, maybe, that might be useful to look at.
Yes, okay, Wolf flow and Healy-Shaw flow.
I have a question. So this is a sequel to your first talk. So
yes.
I would like to understand how this ties in with the character.
Okay, it doesn't to some extent, and it does in a slightly different way. It doesn't directly to the character theory. There's no particular way. what I would say is the following, is that if you take a surface in R3, we saw yesterday one of the things that the key element was to write, from that you can get a map from the surface into the space of oriented lines. The space of oriented lines being a set of all the lines in R3, and the map here is from a point to its normal line, its oriented normal line. And then the weird thing about this is that it has this indefinite metric, plus, minus, minus. It's got split signature, so that's slightly unusual. And then when you pull back this metric to this surface, the induced metric, so the induced metric is Lorentz. So it's a 1-1 metric, except at the umbilic points, and at the umbilic points is degenerate. The metric is degenerate at umbilic points. Right? So these are just some of the geometric facts in the space of oriented lines. Now what we've done here is okay, so one of the things you could think about the oriented lines, this is the space of oriented lines, and the space of oriented lines, I guess you can think of it as four-dimensional space. It's kind of like a geometrized one-jet, first derivatives, being geometrized. Okay, so just loosely you can think of it as a geometrized one-jet. What I have here in this radius of curvature space is a geometrized two-jet. And because it's essentially to be geometrized, you end up now with a two-dimensional space instead of a four-dimensional space. So what we have here is a map from S into this radius of curvature space. Okay, so there is a direct connection between these, believe it or not, a geometric connection. The connection is as follows. If you take this induced metric, and if you look at its curvature form, the curvature 2 form, which is a 2 form in this four-dimensional space, and if you pull this back, so if you pull back this onto the surface, it's the same as the anti-de Sitter metric on R2, on curvature space. So this is F star of the volume form of hyperbolic space, hyperbolic area form. So again, this was our maybe filter or something into curvature space. So what that's suggesting is the picture I drew up there a minute ago. You have this umbilic. The umbilic points are singularities. They're at infinity. This is what they're at infinity. So what we have here is 2 copies of so anti-de Sitter space. This is, you could use either the anti-de Sitter space or you could use the hyperbolic space. You could either use the signature 2, or you could use 1-1. It's the volume form, so it's the same for the area form. It's the same for both. So what you have is a very natural way in which you have a kind of a null structure on the space of curvatures. And an indefinite metric. In fact, it's 2 indefinite metrics glued together at infinity. Right? You have an upper hyperbolic space and a lower hyperbolic space. Now, the surface doesn't really see these things in that way, but it does see the hyperbolic metric. In particular, if you take the isometries, so if you translate horizontally, this is an isometry of the space. If you just translate, the hyperbolic metric is invariant. To translate horizontally, that's equivalent to taking your surface in R3 and moving it parallel to its normals. Right, so this is the same as moving your surface parallel to the normal. Is translating this whole space. So if you take a surface and you translate it out, it's going to just go further and further out here in the convex area. If you kind of shrink it along its normals, eventually it crosses this. This is where it loses its convexity exactly when its diagram touches this. Now to this it doesn't matter, it just sees it go through the whole thing. In R3 it goes inside out and the surface goes crazy. But in this space it's just a translation, horizontal translation. The other isometries that you have for both the anti-de Sitter metric and the hyperbolic metric is scaling about the origin. So that's the same thing. So if you scale, your hyperbolic scaling is exactly scaling in R3 about the origin. So you have 2 classes of isometries for this metric on curvature space, which correspond to geometric translations and stuff in R3. So I can't say that there's any direct connection. You don't really need to know that to do the computations that I just did, but it at least gives you why I call this the umbilic horizon, is because the umbilic points are kind of at infinity in this metric. Right? So it doesn't see them. But then the asymptotics as you go to the umbilic point, that's exactly this fall off, if you like. That's precisely, that does have this nice geometric interpretation in terms of the slope, and then what we've discovered is that the slope determines the outcome of curvature flows. For rotation symmetric ones, if you take, it just entirely depends on the slope, this quantized slope of the diagram or the curve at the boundary, just at these umbilic points. The umbilic points, again, are controlling all of the flow. So that's philosophically at least close to Carly George.
Thanks.
Yeah.